Hi, my name is Mark Evanstein, and I'm going to demonstrate how to compose music using SCAMP, the suite for computer-assisted music in Python. Most algorithmic composition tools dedicate themselves either mostly to sound synthesis or to music notation. The goal of SCAMP is to incorporate both into a single workflow, and to do so in a way that connects the composer to their other resources for playback and notation. In this video, we're going to start with a simple script showing how to play a single note, and gradually build our way up to this. So let's get started. We start by importing everything from SCAMP import star, and then we create a session object called S. Now a session object is kind of like a session in a digital audio workstation. In a DAW, a session gives you different tracks, allows you to manage the flow of time, and lets you record stuff. And same thing here. This session is an ensemble, so it has different instruments. It's a clock, so it allows you to manage the flow of time, and it's a transcriber, meaning that it allows you to note down everything that all of the instruments play and ultimately convert that to a musical score. The next line here, cello equals s.newPart, cello, creates a new part within the session with the variable named cello, and we pass it this string cello to say what kind of sound we're looking for. If we'd given it the string violin, it would look up a violin sound. If we'd given it the string oboe, it would look up an oboe sound. And then we just tell it to play a note. The first argument is the pitch. 48 is going to be the C below middle C using the MIDI pitch standard. The second argument, 1.0, is volume scaled from 0 to 1. In general, I scale things from 0 to 1 where possible in SCAMP. And then the third argument is the duration of the note. So let's take a listen. And there you go. Something important to note here is that the call to play note is a blocking call, which means that you don't finish this line until it's done playing the note. We can play several notes in a row, like so, and we'll try that out. A more efficient way to do that would be to wrap all of this in a for loop. So I'll say for pitch in 48, 53, 67, cello.playNote pitch. And this should do pretty much the same thing. Now this duration is in beats, but by default the tempo is 60 beats per minute, so it's by default in seconds. If we wanted to make the notes shorter, we could do it one of two ways. We could change the length of the notes, or we could change the tempo. Now remember I said that the session is a clock, among other things, so we can use it to change tempo. So we could say s.tempo equals 120 and play it again. And then just really quickly to demonstrate some notation, if I, after creating the cello here, say s.start transcribing, and then afterwards I say s.stop transcribing, this returns a performance object, which is, it's a little bit like a MIDI file, though a lot more flexible. And we can convert that to a score and show that. The call to show here will conspire with the Python library abjad to produce a lily pond score and then open up the PDF. So let's try that. And there we go. If you want to change the time signature or anything like that, that's pretty easy. You just give an argument here. Let's make it a 3/8 time signature. You can also have other time signature combinations. You can have it alternate between different time signatures, but for now we'll leave it at that. Before moving on, I just want to point out a couple more things here. The first thing is that these numbers, these durations, don't have to be nice, easily divisible numbers. They can be crazy things, like if I did 0.7921 or something like that. And I'll just go back to having the default time signature. And you'll see that if I run this, we end up with a quantization. This quantization is extremely customizable. You can choose only to allow divisions of the beat up to a certain divisor, or to prefer simple divisors like 4s or 8s. The other important thing to note is that you don't have to show it using Abjad and Lilypond. One of the really important design considerations in SCAMP was that it would also output music XML, so you could edit it after the fact. So if instead of calling show here, I say show XML, and I run it, then it will try to open it up in Sibelius, which I have open in another window. And there it is in Sibelius, and we can go ahead and change these notes if we want at this point. Okay, so now it'll start to get a little bit more interesting. I've defined here a function called wrap in range, and the idea here is that if you give it a value, it'll wrap it between two different values. So here I'm using it to confine the cello pitch between the C 2 octaves below middle C and middle C. If you go up to pitch 62, which is a D above middle C, it'll get wrapped back down to 38, which is the D 2 octaves below. The basic process here is just that we're constantly adding some interval to the cello pitch, and we're also adding something to that interval. So at first the cello pitch is going to go up by a half step, then a whole step, then a major third, then a perfect fifth, etc. And this is going to allow it to wrap back round to the low register after it gets high enough. The while true here is going to cause the process to go on forever until I stop it. So let's take a listen. So it's a simple process, but the result's definitely starting to get more interesting. As the next step, I'm going to make things a little bit more dynamic. So SCAMP allows you to define envelopes, which are essentially continuously changing values for musical parameters. In this case, I'm using it to define a forte piano dynamic. Down here, instead of assigning a fixed value to the volume of the note that the cello plays, we can assign it the forte piano envelope. Let's take a listen to what that sounds like. I also changed the duration of the note to 2 seconds. So that last example was starting to get a little cluttered, which is why I've put some of it inside of a separate definitions file. From definitions import star imports everything in that file, and those definitions are defined here. We've got the wrap in range function, we've got the forte piano, and then we've also got another envelope, just a straight diminuendo that I've created. And from here, we're going to add a little bit of variation. So I'm going to start by importing a couple of functions from the random module of the Python standard library. Random gives you a random value between 0 and 1, and choice lets you randomly select an object from a list. So now down here, I'm going to every time select a random number and see if it's less than 0.7. This means 70% of the time we're going to do this. We're going to just play our regular cello pitch with a forte piano. The remainder of the time, the remaining 30% of the time, we're going to play a cello pitch using the diminuendo dynamic. And then we're going to wait afterwards. Now I want to mix up a little bit how much we wait. So I'm going to have it choose between waiting 1 second and 1.5 seconds. And actually, while we're at it, let's make the notes have somewhat of a random length as well. We'll make the forte piano notes 1 or 1.5 seconds, and the diminuendo notes, which are kind of arrival notes, we'll make them a little longer. We'll make them some choice between 2, 2.5, and 3 seconds. Let's take a listen to what that sounds like. To take a look at the notation, I'll pull a sort of finished script out of the oven here. And all I've added here is the start transcribing and stop transcribing lines. But then I also wanted to make it so that every arrival note starts a bar. The way I did this is to create a list of bar lines, and each time that we play that note, to add the current time to that list of bar lines. Then there's an option down here where we convert it to the score to give it a list of bar line locations. It's also important that it doesn't go on forever if we want to take a look at notation, so I made it stop after 30 seconds. Let's take a listen and see what it produces. And there we go. A few awkwardly long bars, but we can fix that later. You might also notice that the dynamics don't show up in the score. Dynamic notation will be incorporated in a future version of SCAMP. At this point, you may be wondering how to do multi-part music in SCAMP. And you may also be wondering if it's possible to move beyond mediocre sound font playback. This next step should answer both questions. So up here in this line, we're creating a new MIDI part, which is a part that sends a MIDI stream to an external application or synthesizer. Instead of playing back with sound fonts, it's going to send MIDI messages to this virtual MIDI bus called IAC. Those messages are going to be picked up here by Pianotech. We use the Pianotech instrument down here. Every time the cello arrives at one of the diminuendo notes, we're going to play a sequence of septuplet 30-second notes leading into a half note. I've ensured here that both the start pitch and the arrival pitch are of the same pitch class as the cello. The septuplets, however, are going to vary in a uniformly random way around the start pitch. Now, uniform gives me a random floating point number between two values, so the result here is going to be microtonal. Microtonal playback in SCAMP is as simple as using a floating point number for pitch. Under the hood, SCAMP handles all of the MIDI pitch bend messages and channel management. One last very important point. The arrival note is played with a flag blocking equals false. What this means is that instead of waiting till the end of the note to move on to the next line of code, it immediately moves on to the next line of code. This allows the arrival note and the very next cello note to happen simultaneously. There's another much more flexible way of having simultaneous voices though, which we'll get to shortly. For now, let's take a listen. This next example here doesn't really change anything. All it does is wrap all of the lines of code for the Pianotech upbeat into its own function. Note that we don't move on from this line until the function that it calls is finished executing. However, if we want the function to run in parallel, we can do that. The syntax here is that we tell the session to fork this new function, which starts it as a parallel process. Notice that the final half note here no longer says blocking equals false. Because we still want to align it with the next cello note, I added a wait 0.5 here, corresponding to the half beat that the septuplet 30-second notes take up. These last examples would have sounded exactly the same as before, but now let's take advantage of the parallelism. This code here performs a hopping gesture after the arrival note. It uses the scale class from one of the SCAMP extensions modules to follow a scale based on the cello pitch. The instrument repeatedly hops down 4 scale degrees and then up 1 scale degree, getting quieter each time. And it would keep doing it forever, except that when we want to start a new gesture, we kill the old gesture. This is possible because the call to fork returns a clock corresponding to the forked process. before starting the new gesture, we check whether that clock has something, and if so, stop it. Let's take a listen. The clock on which this new process runs can actually be used within the process if we add it as an argument to the function. I'm going to use that here to do a retardando over the course of the hopping gesture. We do this by setting a rate target. In this case, I'll set it to slow down to 1/4 of the speed over the course of 10 beats. Let's take a listen to what that sounds like. Finally, let's take a look at how the notation for all of this looks. I've added here the start transcribing, and at the bottom the stop transcribing to score show calls. And in order to avoid really long bars, I created a function called doBarLine in the definitions file that adds a new bar line and then tries to make the bars before it a little bit shorter and more reasonable. Finally, I had to add these parameters to the toScore call. Max divisor of 14 allows us to go up to a division of the beat into 14 parts, which is what we need for septuplet 30-second notes. The simplicity preference is also just a little tweak that helps determine how complicated of a divisor we allow for a given beat. With a high simplicity preference, we tend to divide the beat into 4s and 8s and maybe 3s. With a lower simplicity preference, you're more likely to get 7s and 11s. But also, we don't really want to listen to this again. We just want to see what the notation would look like. So in order to do that, we can add a line like this. s.fastForward in beats, and I'll give it some large number like 100. Since the entire score is only 30 beats long, this will fast forward through the entire process and go straight to generating notation. When you're working on a longer piece, fast forward in beats can also be used to skip to a later part of the piece so you can hear it without having to listen to the beginning. Let's take a look at what notation this produces. So you can see the septuplet 30-second notes right here. These quarter tones are our best approximation of the true microtonal pitch, though you can turn on an option to add annotations so you can see exactly what the pitch should have been. Our decelerating hopping gesture looks kind of gnarly, to be honest, but the truth is that this is just a really difficult thing to notate cleanly. So even this notation is a triumph. All in all, pretty good. The sonic possibilities of SCAMP are further expanded by being able to send OSC messages to external applications. Here we create a new OSC part to send messages to Super Collider. And over here, we have a running copy of Super Collider with a synth-def that I've created. The SCAMP utils Super Collider library allows us to turn this synth-def into an instrument that we can play from SCAMP. When we run this snippet of code, OSC receivers are set up to listen for note on and off messages, as well as messages setting the frequency, the volume, and other parameters of the sound. In this case, I've defined crackliness, spread, and pan. Now that things are set up on the Super Collider end, we can go ahead and run it. As you can hear, there are two notes, one at pitch 77 and one at pitch 65. The first one gradually increases volume from 0 to 0.7. The second one gradually decreases it back from 0.7 to 0. This notation is a shorthand for creating a very simple envelope. The first note lasts 5 seconds, the second note lasts 9 seconds. And then in the optional fourth argument to the play note call, we're passing a dictionary of other parameters. These allow us to control the crackliness and the pan and the spread defined over here in the synth def. Now let's incorporate this new form of playback into our composition. We create here the OSC part to send to the Super Collider instrument. And down here we define a function that does more or less the same gesture I just demonstrated. Every time the cello pitch arrives at its diminuendo note, we fork that gesture, so long as it's not already running. Let's see what it sounds like. Now, of course, the crackliness, spread, and pan parameters are not going to be captured in the score. However, they are captured in the performance that was transcribed. Here I chose to save it to a JSON file on the desktop. Let's take a look at what's in it. Here's the cello part. Let's scroll down and find the Super Collider part. There's the piano tech part. And now at the bottom, here's the Super Collider part. And you can see that for each note, the crackliness and the pan, and down here also the spread param, have been saved. This information could later be used to construct some form of score that incorporates these parameters. We now have a fairly interesting musical texture, so the final step here will be to shape that texture over time. One of those powerful ways to do this in SCAMP is to use the envelope class. We've already seen envelopes used to define forte piano dynamics and other continuous properties of note playback. But here we're going to use it to shape the higher level form. I've defined up here the total length of the piece to be 3 minutes, and I've split that length up into 2 sections based on the golden ratio. I've then defined a number of different envelopes for different aspects of the music. This script is going to be imported by our main script, but when it's run directly, it'll show a plot of each of those envelopes. Let's take a look at that. We'll gradually incorporate each of these different curves into the music. To start with, we're going to incorporate the cello continue probability and staccato probabilities. So we'll go over here, and at the bottom, you can see that I commented out the lines that fork the piano tech and Super Collider parts. Instead of having a fixed 70% probability of the cello continuing on to another forte piano, I've now made that probability a lookup to the cello continue probability envelope, plugging in whatever the current time in the session is. At the bottom here, I've added a possibility that after each diminuendo arrival, there's a short staccato pickup to the next set of notes. Notice how this is done. Articulations like staccato are one of the things that we can put in the play note call's optional fourth parameter. This will render in notation as a staccato dot, and it will also cause the note to be played back a little shorter. In the staccato probability curve, I've made it so that these staccato notes show up more towards the end of the piece. So to take a listen to it, I'm going to use the fast forward in beats and place us somewhere around 2.5 minutes in. Let's take a listen. Now, to my taste, that staccato could have been a little bit shorter. And it's actually possible to modify the way in which it's played back. The way we do this is we look at the playback settings, which has an adjustments dictionary inside of it, and we set the value for staccato to be to multiply the length by a factor of 0.3. If we wanted, we could use this process to make staccato notes come out louder, or even a different pitch. But let's take a listen to how this sounds. That's a little bit crisper. The next thing we might do is add a little bit of tempo variation. You can see here at the bottom that I still have the Super Collider and Piano Tech parts commented out. And I've added a new line up here, set tempo targets. Again, because this has to do with tempo and time, it's a call to the session, since the session is a clock and manages time. The starting tempo is the default tempo of 60, and I've set it here so that it'll reach the tempo of 150 at the golden ratio point, and then return back to a tempo of 60 at the very end. Let's take a listen to it first at the beginning. And now, somewhere around the golden ratio point, which is probably about beat 110 or something like that. So it's significantly faster. I think with the other parts, the tempo change will be more noticeable. Let's take a look at what this means in terms of notation. I'll change this to fast forward 1,000 beats so that it'll definitely get all the way to the end of the piece. And let's see what we get. So as you see, you get an accelerando, and helpfully we've got some guide marks here telling us what tempo we're at any given point. We reach the goal tempo of quarter equals 150 right here and immediately start slowing down. And then here we reach the final tempo of 60. But wait, why is it not at the end? The reason is that the piece ends after 180 seconds. But these tempo targets are in terms of beats. Since on the whole our tempo is faster than a beat per second, we will reach beat 180 significantly before 180 seconds. However, one good way that we can fix this is to add the keyword argument here, duration units equals time. This will cause this number to be interpreted as 180 seconds rather than 180 beats. Let's take a look at the new notation. Scrolling down, we can now see that it reaches 60 beats per minute, exactly at the end of the score. That said, this ending looks a little bit abrupt. The next step tries to remedy this. Scrolling down to the bottom here, I've changed it to an infinite loop, but then added this end condition. If we've passed 180 seconds and the cello pitch is about to be a C, then we break out of the loop and skip down to this final note, a 4-second low open C string with a diminuendo. We also then add a final bar line. Let's take a look. And as expected, it ends right here on a low C. Now for this final step, I'm going to pull out all the stops. Here in the Piano Tech part, I've animated the length of the hopping gesture so that it gets longer and shorter over the course of the piece. I've also changed how much that hopping gesture slows down, depending on where we are in the piece. Since this only occurs when the cello reaches its arrival diminuendo notes, and since in the middle, when I want things to be most active, that actually happens least often, I've actually added another filler gesture to occur in between. This plays some rising staccatissimo quintuplets, making use of the play chord instead of the play note call. For the Super Collider part, I've animated the gesture length, the register, and also how crackly it gets. And then finally, I made it so that the Super Collider part doesn't start until 20 seconds in, and the Piano Tech part doesn't start till 40 seconds in. Now I want to do things a little differently here because I want to be able to watch the score as it plays. Since the music would be different every time because of all of the calls to the random library, we can fix that by giving a random seed. This will cause the piece to render identically every time. I'll add our fast forward in beats trick and go ahead and generate the score. When it's a whole 3 minutes of music, it can take a little while to generate the score. And there we go. You see that the Piano Tech part and Super Collider parts are silent at first, that the Super Collider part comes in first. Now, unsurprisingly, a lot of the substance of the Super Collider part can't really be notated, but it does do a good job of notating the glissando. Let's take a listen and follow along. I'll delete this fast forward in beats, and here we go. Note, by the way, that the starting tempo is written as dotted quarter equals 40 instead of quarter equals 60. That's the same tempo, it's just a 3/8 bar. There's that extra filler gesture that I added. Sometimes the hopping notes get put together into a chord. If we change the quantization, that could be fixed. There's some crackliness to the Super Collider gesture there. Again, quantization issues here. The Super Collider part's getting lower in register. And there you have it. Writing a short, sort of a toy piece in SCAMP, but I hope this gives you some idea for the potential of the framework, and thanks so much for watching.